Hi there. In this lesson, we're going to take circular motion and the equations of simple harmonic motion. To explore the properties of simple harmonic motion, we must express the displacement x of the oscillating body as a function of time. So, this means x, if you write it as this, it shows that x is a function of time. So, what I'm trying to say is we have to express displacement x of that oscillating body as a function of time, t. The second derivative of this function, written as d square x over dt square, must be equal to minus k over m. As we showed to us in our previous lesson, the formulas for constant acceleration are no help because the acceleration changes constantly as the displacement x changes. So instead, we'll find x as a function of t now as a function of time by noting that simple harmonic motion is related to uniform circular motion. Let me explain what I just did here. This figure here shows a top view of a horizontal disk of radius a, which is this a, with a ball attached to its rim at point Q, which is this point Q. The disk rotates with a constant angular speed, which is W here. Okay? Now, this speed is measured in rad per second. So, the ball moves in uniform circular motion around the disk. Okay, now, this is the horizontal beam. This is our light beam. So, a horizontal beam casts a shadow of the ball on a screen. This line I drew here with the green marker is showing the screen. Okay, let me indicate it. So, these are illuminated screen. We're doing this so that you can understand the whole concept of what I've been talking about on simple harmonic motion and a body actually undergoing simple harmonic motion. But in this case, I'm going to combine it with that of circular motion. So just follow me closely. So this light beam casts a shadow of the ball on the screen. Yeah? The shadow at point P oscillates back and forth. Oscillates back and forth. Okay? That's what I drew here. As the ball moves in a circle. So, as the ball is moving, that is this ball at point Q, as it's moving in this circle, its shadow is moving back and forth on the screen. Now, we then arrange a body attached to an ideal spring. That is this point here that I drew. This point here, down to the fixed point. Okay, so that the body oscillates parallel to the shadow. So that was just the essence of doing that. Now we'll prove that the motions of the body and of the ball's shadow are identical if the amplitude, which is A, which the ball's shadow is moving back and forth, if the amplitude of the body's oscillation is equal to the disk radius A. This is why we didn't use the symbol arrow, okay? So we'll prove that if the amplitude of the body's oscillation is equal to the disk radius A, and if the angular frequency 2 pi f of the oscillating body is equal to the angular speed W of the rotating disk. So we can verify this remarkable statement by finding the acceleration of the shadow at point P and comparing it to the acceleration of a body undergoing simple harmonic motion as we gave in equation. Okay, let's call this equation. I think we called this equation 2 in our previous lesson so that we can be making reference to it. Okay, the circle in which the ball moves so that its projection matches the motion of the oscillating body is called the reference circle. So we call the point Q the reference point. So Q now on the reference circle, the reference points. We take the reference circle to lie in the XY plane. Now let's take another drawing to show this. So if we have the reference circle like this, and we have the xy plane, the xy plane, with origin at this point 0 here, right? Let's show our ball now, okay? So the ball is at a point here on the circle. Call this point Q. Okay, so this is the radius of the circle A, right? Okay. So now this is the shadow. Let's show the shadow in which the ball makes on the screen. There's the shadow. Okay. So this is the distance from the origin O. Then we have the path in which the ball is moving. So what else is left? Okay. So this is point P. That's the ball shadow. Point P. Then, okay, let me darken this so you know it is shadow. Okay. So now the ball shadow will move back and forth, like so, back and forth in the x-axis. So we have it to be x. So this is the x-axis, right? So we have x here equal a cos theta, because you can see that the ball makes an angle theta with the horizontal plane, this angle, we call theta. Now at time t, the vector OQ from the origin to reference point Q makes an angle theta with the positive x-axis. As point Q moves around the reference circle with constant angular speed W, vector OQ rotates with the same angular speed, okay? Such a rotating vector is called a phasor. This term was in use long before the invention of the Star Trek stun gun with a similar name. So we'll use phasors again when we study alternating current circuits much later. The x component of the phasor at time t is just the x coordinate of the point Q. So x coordinate, like we gave here, is given as a cos theta. Take note of it. So let's call this equation A. This is also the x-coordinate of the shadow P, okay, which is the projection of Q onto the x-axis. You can see from this illustration, shadow P, okay, is a projection of Q onto the x-axis, right? Hence, the x-velocity of the shadow P along the x-axis is equal to the x-component of the velocity vector of point Q. And the x-acceleration of P is also equal to the s-component of the acceleration vector of Q. And since point Q is in uniform circular motion, its acceleration, given as AQ, is always directed toward O, okay? So, furthermore, so this acceleration is always directed towards O like this. So let's say this is the acceleration AQ, okay? So always directed towards O. But furthermore, the magnitude of AQ is constant and given by the angular speed squared times the radius of the circle. So it is constant, take note, and further given by the angular speed, which is W, right, squared times the radius of the circle, which in this case is A. So the s component of AQ is AX, and this equals AQ cos theta. You don't really need to bother yourself too much about deriving all these formulas. All you just need to know is how and when to apply them. Okay, you just need to be able to understand how this formula came about and what it is related to. Then you can pick yourself up from there. So AX now is given as minus AQ cos theta. Note the x component of AQ now, okay? So we have AQ cos theta. We will combine this with equation A and B. Let's call this B. So if we combine equation A and B, we get that the acceleration of point P is, so AX equal, where you see AQ, you put W square A. We have minus W square A cos theta. Okay? Minus W square A cos theta. Or you can simply put AX equal minus W square. When you see A cos theta, you put X because X is equal to A cos theta, okay? So we put down X. So we have X. As simple as that. Let's call this equation C and D. Let's start numbering our equations because we're eventually going to reference to them. So the acceleration of point P is directly proportional to the displacement X, right? As you can see here. And always has the opposite sign. That is why we have minus here. These are precisely the hallmarks of simple harmonic motion. Equation D is exactly the same as equation 2 for the acceleration of harmonic oscillator. What did we give as equation 2? Let's check that. So you guys don't start. Okay, so this is equation 2. So it says that equation D, right, is the same, the acceleration of a harmonic oscillator, provided that the angular speed W of the reference point Q is related to the force constant K and mass of the oscillating body by this, by W square equal K over M. Then we can write this as W equal root K over M. Okay, so take note of this. So let's call this equation E. So we have been using the same symbol W for the angular speed of the reference point Q and the angular frequency of the oscillating point P, right? The reason is that these quantities are equal. If point Q makes one complete revolution in time t, then point P goes through one complete cycle of oscillation in the same time. Hence, t is the period of the oscillation. During time t, the point Q moves through 2 pi rads, okay? The point Q moves through 2 pi rads, so its angular speed is W equal 2 pi over t. But this is the same for the angular frequency of the point P, which verifies our statement about the two interpretations of W, okay? You can take your time to go through this again to understand what I just explained. This is why we had to introduce angular frequency, okay? This quantity makes the connection between oscillation and circular motion. So we interpret equation E. As an expression for the angular frequency of simple harmonic motion for a body of mass m acted on by a restoring force with force constant K. When you start a body oscillating in simple harmonic motion, the value of W is not yours to choose. It is predetermined by the values of K and M. Now, the units of K are Newton per meter or kilogram per second square. So, K over M is in kilogram. So, we write K over M, okay, equal kilogram over S power of square. That's kilogram per second square over kilogram, which is the unit for mass. So we're trying to get the units now, the total overall unit, okay? So if we put this up, kilogram over second square, this becomes divided kilogram, right? So we have this to be kilogram per second square times 1 over kilogram. Taking the inverse now is what we did. So cancel out. We have finally 1 over s square. So this is also equal to, as well write this as s per square, s is power of minus square, which is per second square. That is how you interpret it. So if we take the root from the formula root, okay, so w equal root k over m, right? So if we take the root of this, to get the exact units, we get this now be in bracket 1 over 2, right? This is the same thing as root s minus 2. Take notes. So we have it to be s minus 2. When you take the inverse of this, you get 2 minus. Okay, so this is the same thing as 2 minus 1. Okay, so you go further to solve, you get s minus 2, taking their powers now, plus 2 minus 1. When you do this, you have x raised power of minus 1. So this is the exact units for that equation. Okay. We can either say this to be per second or more properly radian per second. Okay, because this is an angular frequency we're talking about. So we can either put this to be this or say rad per second. Okay. According to our previous equations, the frequency f and period t we wrote as f equal 1 over t, right? And t equal 1 over f. You remember this, right? So if we put our formula or the relation we got for angular frequency into these relations, recall in our previous equation which we gave that f is a reciprocal of period t and vice versa, okay? So we also said along the line that f is equal w over 2 pi, right? When we're trying to relate frequency and angular frequency. If we put the equation for angular frequency w into this relation, we get f will equal 1 over 2 pi square root k over m. Okay? Then for period t, you know period t is the inverse of f. So let's say t, which is the inverse of f, this will become 2 pi over w, right? So if you put, where you see w, put root k over m. So you know it will be an inverse as well. So you have it to be 2 pi root m over k. And this is simple harmonic motion. Equation for a simple harmonic motion too. Okay, let's call this equation G. Okay. So we see from equation G that a larger mass m will have less acceleration and take a longer time for a complete cycle. That is the interpretation, okay? In contrast, a stiffer spring that is one with a larger force constant K, exerts a greater force at a given deformation X, causing greater acceleration and a shorter time T per cycle. Note, don't confuse frequency F and angular frequency W equal to pi F. You can run into trouble if you don't make the distinction between them. Frequency tells you how many cycles of oscillation occurs per second, while angular frequency tells you how many radians per second this corresponds to on the reference circle. And so in solving problems, pay careful attention to whether the goal is to find F or W. With this, we have come to the end of this lesson. I had to go through this long process to enable us know how the simple harmonic equations came about to avoid confusions when you eventually come across them. If you have any questions, kindly drop them in the comment section below. See you in the next lesson.